In this video, we will give some examples on how to compute limits of sequences. We will not appeal to the precise definition of a limit, but only to our intuition. From the previous video, we know these two limits. The first limit is based on the intuition that n has no bounds. It can be as big as we want. Other ways of saying this is that a sub n does not converge, or that a sub n diverges, or that the limit of a sub n does not exist. Now, the second limit is based on the intuition that as we increase the value of the denominator of the fraction, the value of the fraction itself gets smaller and smaller and closer to zero. You may think that this is not a very satisfying way of determining the limits of a sequence, and that's true. To rigorously prove these limits, we need to first discuss the precise definition of a limit, which is a rather subtle concept. So we reserve that for a future video. We now look at this limit. This is basically a sequence of alternating negative ones and 1. So the sequence just alternates between these two numbers. We see that if n is even, for example 2, then the value is just 1. That is true for any even value of n, for example 100 or 1,000,000. It's just equal to 1. And when it is odd, for example 101 or 1,000,001, then the value is -1. Because it just alternates between these two values, the sequence does not really approach a single number. It just goes like a wave. And so we say that for this sequence, the limit does not exist. Now we go to the next limit. If we look at this expression of the sequence, we can see some very familiar expressions. For example, we have seen this 1 over n in a previous slide, as well as this -1 to the n. And we also recall that we can do arithmetic operations on limits, so that the limit as n approaches infinity of this whole sequence can be expressed as the sum of limits. So we can write the limit of a sub n as n approaches infinity can be written as the limit of n as a limit of 1 as n approaches infinity, plus the limit of 1 over n times -1 raised to the n plus 1 as n approaches infinity. The first term is rather obvious. Because 1 does not depend on the value of n, it doesn't matter whether n becomes very big or very small. The limit of 1 is always 1. The second term, on the other hand, depends on n here in the denominator and n here in the exponent. We know that the value of -1 raised to the n fluctuates between -1 and 1. And so we might be tempted to think that this limit also does not exist. However, we have to remember that the limit of 1 over n is actually 0. If we have a number that fluctuates between -1 and 1, and we multiply it with a number that gets smaller and smaller, then what we get is actually another number that fluctuates between positive and the negative quadrants. But at the same time, the absolute value gets closer and closer to zero. For example, we can have 1 over 100 and negative 1 raised to the 101. And because this is an odd number, we will have a negative value. And when we do that for 101, we obtain this value. So although the signs are different, clearly their absolute values are getting closer and closer to zero. And so we can say that this whole expression approaches zero as n approaches infinity. Again, that is because this value in the denominator forces the whole term to get smaller and smaller, even as it fluctuates between positive 1 and negative 1 in the numerator. And so the limit of the entire sequence can be regarded as 1. Now, the next limit is rather intuitive because we can see that the numerator and the denominator are almost the same number. They differ by 1, only by 1. For example, we may have 9 over 10, so that the numerator is only 1 less than the denominator. Then for n equals 100, then we have 99 over 100. And if we go to 1,000 for the denominator, the numerator is 999. You can see that as we increase the denominator, the numerator also increases and the difference between them remains 1. And so the whole fraction actually gets closer and closer to 1. And so we expect the limit to be close to 1 or 1. Let's do this using the arithmetic operations and limits. So we write the limit as n approaches infinity of a sub n equals, we will do the division. And so the limit becomes 1 that equals the limit of the expression 1 minus 1 over n. And now we can get the difference of limits, which is just as follows. And again, we know that this term here is independent of the value of n. This will always be 1 because it is a constant term. And so we have 1 on this part. And on this part, the second term, we have seen this limit in the previous slide. And we know that this is 0. This expression 1 over n approaches 0 as n approaches infinity. And so our final limit is again 1. And finally, we look at this limit, which is the difference of two radicals. Again, if we first think about the intuition of the problem, we see that the two expressions, the two terms of the expression only differ by 1 inside the radical sign. And so if we have 101 here, then we have 100 here. And if we go bigger, let's say 10,001, then here would be 10,000. Many of you will realize that this difference becomes smaller and smaller because as you increase the value of n, 1 becomes less and less significant compared to the values of your n. And so we expect that this term, the first term, will be getting closer and closer to the second term as we increase the value of n. And so we expect the limit to be very close to 0 if not 0. And if we will do it using the arithmetic operations or algebraic operations that we have seen in the past, then we first write it this way. However, we see that if we just substitute the infinity symbol here, we will not get any value. We just get an indeterminate value. And so a trick we can do is to rationalize the numerator by multiplying it with the conjugate. And so we perform the following operation. This is simply a multiplication of both the numerator and the denominator by the same quantity, which is the conjugate of your numerator. And if we do that, we obtain the following limit. The numerator now becomes a difference of 2 squares because it is a product of this expression and its conjugate. And so that becomes n plus 1 minus n. And the denominator is simply as follows. In the numerator, both n's will cancel. Intuitively, we can see that as n approaches infinity, then the denominator becomes very, very big. And in the same way that we reasoned that the limit as n approaches infinity of 1 over n equals 0, we can also reason that this limit also is 0. And so this is our answer for this problem. In this video, we calculated these limits. We relied on intuition to compute limits 1, 2, and 3. Then these limits 1, 2, 3 and algebraic operations on limits were used to compute 4, 5, and 6. We noted that the only way to have a rigorous proof for limits 4, 5, and 6 and 1, 2, and 3 is through the precise definition of a limit, and that we shall discuss in another video. In the next video, we give more moderate rather than easy examples of limits.